All right, let's debrief the important things that I hope that I led you towards during these scenarios. And again, what you're looking at here, you're not looking at, oh, here are steps for how to do a particular kind of problem. It's more like I want to just show you a bunch of scenarios, because like when you're in the wild, you don't know what kind of situation you might have to handle. So it's like we're kind of practicing by seeing different situations, noticing the things that might be relevant or not relevant, learning how to think about each one. So don't try and like grab onto these like these are the answers. You want to think about what you're trying to take away here is not steps for what to do. You're trying to take away concepts, particular things to pay attention to, that sort of thing. All right, so we're trying to find a cubic that fits these 3 points. So we're like, yeah, all right, let's use root form, x minus 3, x minus 5, x minus 9. Oh, but we got this point way up here at 10. So let's just add a y-intercept of 10. Why doesn't that work? Well, the easiest way to see that it doesn't work is let's just plug in x equals 3. We know that if the curve goes through all these points, x equals 3, the y value should be 0. So if x equals 3, this term is 0, and these terms aren't, but you're multiplying them all together, so we've got 0, but we're adding this 10 on the outside. So this equation would actually give us a y value of 10 when x equals 0. A different way of thinking about this is what you do when you add the plus 10 isn't just magically giving it a y-intercept of 10. What you're really doing is shifting it up by 10. So without the plus 10, yes, indeed, we are defining a curve that goes through those 3 roots. But as soon as you add the 10, now the whole thing is shifted up by 10. So these 3 values end up at 10. And you could figure out what the y-intercept was by plugging in x equals 0. It would be negative 9 times negative 5 times negative 3 plus 10. So actually, we'd end up with quite a large negative number down there. Okay, so what could we do instead? One thing we could do instead is we could keep the roots, but we could add a scale factor and solve. So if we're adding a scale factor and solving, let's make the y value 10, the x values are 0, and so now we have, let's see, negative 3 times negative 5 is negative 15 times negative 9. Nope, sorry, that's positive 15, but then times negative 9 makes the product of all 3 negative again, and then k. I'm going to show you, a lot of you, I think, multiply, like you want to be working with a simplified number all the time, which is sometimes helpful. I intentionally didn't multiply 15 times 9, not only because I don't know what that is in my head and I'm lazy, but also the laziness is really going to pay off. If I divide by, think about this as being a number. If I divide, look what's going to happen. I've got negative 15 times 9, and now all of a sudden this is easier to simplify by hand without a calculator. So 10 and 15 both have a common factor of 5. So if I divide the top by 5, it gives me 2. I divide by the bottom by 5, that gives me 3. And so now I've got 3 times 9, which is 27, and that I do know. So negative 2 27ths. So rather than going to all the trouble of multiplying 15 and 9, and then maybe feeling like you want to simplify after you've done the division, just keep your numbers kind of small and easy to work with, and hopefully things will end up canceling each other or simplifying in some other way, and that'll give you an answer. All right. Oh, great. So we're done. It's always good to do some sense checking. So you can plug in x equals 3 and see, does it actually give you a root? And indeed it does, because we're just multiplying everything now. You should think, like, why does it make sense that this sign should be negative? But other than that, I think that's a good one. Oh, gut feels. Do you think there are other cubic equations which also fit these points? I hope that your gut feel says no. And we don't really have good tools for articulating exactly why. But the kind of idea is, if we're sending a cubic through 3 points, cubics have enough flexibility to do that. But as soon as we send it through a 4th point, that forces all the, we only have a certain number of transformations we can apply to the cubic. And so applying a transformation that forces it through the 10 means that we don't have any more freedom. If we were going to change the cubic in any way from here, it would mean that it wouldn't be part of one of those points anymore. We'll think more later about kind of how can you think about this question a little bit more rigorously, but I just wanted you to, you should start developing a feel for these things, and this is part of developing the feel. All right. Fifth degree polynomial that goes through 3, -7. So your partner says, look, we can find lots of different equations that work. Let's just do x minus 1, x minus 2, x minus 3, x minus 4, and then scale them by k, and then solve for k. Is that going to work? And the answer is yes, absolutely that's going to work. What a good idea. Almost. Let's think this through. So what would this first one look like? Here, it's like I take a fifth degree equation, which looks like this, and I'm shifting it right by 1. Let's put in 3, -7. So here's 1, 2, 3, and -7's way down here somewhere. So I got my fifth degree equation. I'm shifting it right by 1. So right now it looks like this. And then the question is, could I introduce a scale factor k that would force this shape through that point? If k is negative, that would flip it upside down. And so the answer is yeah, absolutely. In fact, let's just do 1 to convince ourselves that's going to make sense. So here I've got a y value is -7. Here's k. X is 3, so 3 minus 1 is 2. 2 to the 5th is 32. So that means k is -7 divided by 32. Cool, and that's done it. And so what we've done is we've got a curve whose, quote-unquote vertex is here, but that goes through the point that we want. So that's going to work for all of these except for one of them. And if you kind of thought these through clearly, hopefully you realize this one it won't work for. And the reason why is because we've taken this shape, we've shifted it right by 3, so now it looks like this. But there is no scale factor that we could apply to this that would force this point through that point, because they have the same x value. This might be clearer if we actually try and solve for k. Let's try and solve for k in this case. So y is -7, k, but then we've got x value is 3. 3 minus 3 is 0. So now it's like k, some number times 0 is -7. But obviously no number times k times 0 is -7. So these vertical scale factors work for all of them except this one. This problem's really kind of if you thought through this, that shows that you're thinking flexibly and well about this. If you didn't think your way through this, you should consider that you might be trying too much to filter for steps. You might be too much thinking like, what do I do? But good mathematicians never start with the question, what do I do? They always start with the question, like, what is going on here? How can I make sense of the situation? And making sense of the situation is all this stuff we've been doing. It's like using multiple representations. It's like thinking about what if. It's being able to kind of think flexibly rather than pattern matching and saying, yes, I can use this process like a robot to find the answer. Okay, cool. So the answer is this works great for all the values, or for all the possible shift amounts except for that one. What other things could we do to fit fifth degree equations through that point? Well, let's think. So we could we do this? Could we do x to the fifth just times a scale factor without shifting it? Yeah, I think that's going to work. What about, let's think about what other transformations we could do. We could do, oh, here's an easy one. We could just shift it immediately right by 3 and down by 7. And that would be sort of quote-unquote vertex form. What else could we do? We could, could we use root form? I think probably. Let's just make a bunch of roots. So x minus 1, x minus 2, x minus, I don't want x minus 3 because the x value of 3 needs to be the point down there. So let's do x minus 4, x minus 5. So let's see, this is, now I've got, imagine multiplying this all out. You have an x times an x times an x times an x. So that would be x to the 4th. So now I could just I guess let's get a fifth one in there and then introduce a scale factor. So now I would have 5 points that are roots, and I would scale it so that the sixth point would go through there. You undoubtedly have other things that you thought of, so there are lots of things you could do, but the point of this exercise is, like, do you run out of ideas immediately, or can you think creatively? Can you think about a bunch of things that kind of would fit this scenario? Okay, this problem got a little silly because I was writing it when I was sick and in the nighttime. What in the world? Oh yeah, all right, I remember. So, lest my erstwhile powers elude me, 710 appears to satisfy our need. So here's 710. Wait, our need for what? Vertex form. It appears to satisfy our need for a vertex. So the question is, could we make this the vertex? And the answer is no, we can't. Because remember, for a quadratic is symmetric around its own vertex. So if we made this the vertex, it should be the same distance to this point and this point, since they have the same y value. But it's not. Here we've got 1, 2, 3, 4. Here we've got 1, 2, 3. So that's why that can't be the vertex. Okay, so let's do a different idea. Let's imagine we're going to shift all of the points down by 4. So this point ends up here, this point ends up here, this point ends up here. So there's our new version. Could we fit a curve through this? And the answer is yeah, we definitely could. Let's see, I'm trying to figure out where would the vertex actually end up. Like here, right? So the vertex would be exactly halfway between those two roots. So let's pretend we did that. Well, no, sorry, let's actually do that. So if we've got these two roots, one of the roots is 3, one of the roots is 10. Cool. We need to fit it through another point. So let's add a scale factor for k. K here is 7, 6. So if I plug in 6 for my y value, and 7 for my x value, so 7 minus 3 is 4. 7 minus 10 is negative 3. Does that make sense? Yes. Okay, great. So this is negative 12. So that means k is 6 divided by negative 12, which is negative 1/2. Cool. So we found an equation that works. But wait. The equation that we found is an equation not for our original points, but it's for these points. So how can we make a curve that fits the original points? Let's rewrite it over here. So x minus 3, x minus 4. Well, remember, to get the points where we knew what the roots were, we shifted down by 4. So now let's just undo that. Let's shift it back up again by 4. Ta-da! So this is an example of a whole bunch of strategies that are based on the idea, if the information doesn't fit the equations that you know, transform the problem. Like, apply some transformation so that the information you have does fit an equation that's easy to find, and then transform it back when you're done. And this is going to be used a lot in a particular unit in calculus when you're finding the volumes of three-dimensional shapes. This is going to be a key strategy in that unit. Okay, let's pretend that you didn't think of that trick. What's something else you could have done? Well, something else you could have done is set up a system of 3 quadratic equations, solve the system, just like we did at the bottom right side of the original notes. Just in case this was a little bit unclear, what you could do here for the experts, this is a generalization of the strategy. So if I have 3 points like this, there's no vertex I can find. I can't shift it down by a single amount to get 2 roots. But what I could do is I could imagine taking my curve f of x, which is this imaginary one I'm trying to find. It's not imaginary, it's this unknown one I'm trying to discover. What if I shifted down this parabola by an amount corresponding to this line? Like, what does it mean to shift down a parabola by a line? Well, remember, for particular values of x, L of x is just a number. So what is L of x when x equals 3, for example? Well, let's look at the y value at the line. So when x equals 3, the y value at the line is 4. And if I take my parabola and I shift just this point down by 4, it gives me a root. What would happen when x equals 4? Well, on the line, I have something a little bit larger than 3. So I would take the point on my parabola and shift it down by an amount that's, it's a little bit larger than 4. And so I'd shift it down by an amount that's a little bit larger than 4. So here's like 1, 2, 3, 4, a little bit larger, so about here. So the idea is each x value, the height of the line tells you how much you're shifting that point of the parabola down by. So you're shifting the parabola down by a different amount depending on what x coordinate you're at. And so you can sort of imagine, it's not quite like rotating it, but it's a little bit like rotating it. So this point is going to end up at a root. This point is going to end up at whatever the y value is here. But now you've got a situation that's just like up here. You can use root form. So here it was convenient to subtract by a constant amount to get 2 roots. Here you have to subtract by a non-constant amount in order to get 2 roots. But then once you have an equation that has the 2 roots in it, then you just add the equation that corresponds to this line to move everything back up to where it was originally. I saw this technique used not for the purposes of calculation, but as a conceptual argument in a proof in one of the most important theorems in calculus one time, actually. So this general idea that you can transform by things that aren't constants. You could subtract an equation from another equation to force things to look the way that you want. Very powerful idea.